So hello and welcome again to our second session for today. This session is titled Fate and Exposure Assessment, and it will be presented by our colleagues Teresa Fernandez from Heriot-Watt University, Socorro Vasquez from Leita Technological Center, Sam Harrison from the UK Centre of Ecology and Hydrology, and Joris Quick from the RIVM National Institute for Public Health and the Environment. In this session, we will focus on recent developments in the assessment of fate and exposure of nanomaterials. And to start with, we will play a couple of short introductory videos of this topic, followed by a live Q&A session. So please make sure that you use the live Q&A chat box to post your questions during the presentation so that our speakers can address them. And then we'll continue with another interactive exercise. And now I give the floor to Teresa.
Everybody, welcome to the Fate and Exposure Assessment of Nanomaterials session. And the session will be contributed to by 4 people: myself, Teresa, working at Heriot-Watt University in UK, Soco Vasquez, working at Leita in Spain, Joris Quick, working at RIVM in the Netherlands, and Sam Harrison, also working in UK at the Centre for Ecology and Hydrology. So this is the way we're going to work the session. I'll start a quick introduction to the topic, and this will be followed by Sokos talking about likelihood as well as routes of exposure to nanomaterials. Joris and Sam will focus on modeling. Joris start introducing the topic, and Sam providing a little bit more depth to the complexity of this field. You will be able to practice for yourselves the concepts that we'll be describing and discussing, and then we'll be discussing the results of your exercise and wrapping up with the lessons learned. So you've read the exercise. As I said, it will allow you to test some of the concepts we're going to introduce here. So hopefully you're able to follow instruction and download the model without any problems. So why nanomaterial first and exposure assessment? Why should we be concerned with that? Obviously, nanomaterials are going to be quite different from conventional materials. So they are, as we'll say, they are particulate material, and they are small materials as a starter. So they're not going to disperse as well as conventional chemicals, and because they're so small, they obviously will have a different fate when compared, and potentially impact it when compared with larger materials. So here you can see there's such a diversity in terms of size, for example, in terms of shape, in terms of actual composition, also surface covering. Different surface coatings, for example, are very much in practice in the available nanomaterials. So very large diversity, and so it is important to understand what happens to them in the environment, and also how they might affect. So you can see here they are incorporated in a variety of products. In order to do so, you will need to produce them, you need to incorporate them in these materials, and then during their use or after their use, they might end up in the environment directly through fragmentation, for example, or if they are part of sunscreens, they might end up in the water, etc. But often they are products that end up disposed in some way into the environment, and then they might leach again. So it is important for us to understand the different steps and how the diversity of nanomaterials may actually lead to different types of fates and exposure. Of course, the manufactured nanomaterials are just a part of nanomaterials might exist in the environment. Some of them, as I said, will end up in the environment at the end of life or during use, but you might also find different types of accidental spills leading to exposures, or those products ended up in the environment and leading to different types of the exposures. On the environment, so I've already talked about the diversity. On the environment, they might suffer or go through a variety of transformations. This might depend on the receiving environment. If it's salt water, is for lower pH or higher pH. If it's a higher abundance of organic matter, for example, in soils or waters, all of that will affect the transformation these nanomaterials might go through and where they might end up. some of these transformations might actually be mediated by organisms, such as microorganisms, for example. So understanding these and some of the modeling that we will cover in the next presentations will help us to elucidate some of those steps. And of course, very importantly, is to understand what will happen once you actually have all these transformations. What will happen when organisms get into contact with these nanomaterials? This might be in soil systems, for example, where you have plants, and this might have links with agriculture and maybe inputs into the human food chain. You'll have other types of organisms living in these systems, such as worms, which provide a very important nutrient cycle, for example, in soil systems. Will they be affected? In the aquatic systems, you might have impacts or at least encountering, primary producers, secondary producers, and you might have, the whole food chain becoming in contact with these available nanomaterials, which would have been transformed somehow. This might be impacting over different generations, as you can see here. There's a possibility of that. And of course, when nanomaterials get into the organisms, they might lead to a variety of effects, which might, be impacting respiration, for example, might impact detoxification, might impact might lead into genetic toxicity. So a variety of effects might take place within cells, within tissues, within organisms. So understanding fate and effects of fate and exposure to nanomaterials is instrumental to allow us to assess what hazard might take place when organisms are put in contact with nanomaterials in the environment. So this concludes my presentation, and I'll pass on to Soko for the next step in this topic.
Hello, my name is Socorro Vázquez Campos. I'm from Leitat Technological Center, leading the group of human and environmental health and safety in this research center. And today I will talk about release and exposure along the life cycle of nanomaterials and nano-enabled products. I would like to start with an introduction of the terminology. So the term release refers to the liberation of a nanomaterial during a natural or technical process along the life cycle that takes place along the life cycle at any stage of the life cycle of the nano-enabled product or nanomaterial. Then the emission is the transfer of this liberated nanomaterial or substance to a compartment where it can reach a receptor. And this emitted or liberated nanomaterial then suffers the transmission towards the receptor, and then the exposure is when the nanomaterial come into contact with the receptor, and the receptor can be the human or the environmental species, and possibly through any route of exposure. During this transmission of the liberated nanomaterials, there can happen a lot of transformation and the transport of these nanomaterials in the compartment or in the environment, and this is known as the fate processes that take place during this transmission step. All these events are linked to each other, and any of these events cannot take place if the previous one didn't happen before. So they are subsequent to each other. So then there is a release of nanomaterial, then an emission, and these emitted particles end up to be the exposure particles that going to the target receptor, human or environmental species. So continuing with the introduction, I would like to explain on the life cycle perspective that nanomaterials are generated first during a process that takes place to synthesize these materials. Then they can be manufactured into to be ending up being an article or a product, and then can be used during the by the consumers, and this is during their service life is this use phase stage of the life cycle. And then when they are already used and their service life is finished, then it comes to the end of life processes, which means either waste the product or the article or recycle this article into something else. And all these life cycle stages, during those stages, many processes can take place that can modify and can influence the releases of these nanomaterials in each of the stages. Here are some examples of these processes that we also call it activities that they take place during the synthesis, manufacturing, use phase, or end of life. And during this, we can monitor the nanomaterials releases, but of course, there is some of the properties of these processes will influence this release during the life cycle stages. So then, of course, during these life cycle stages, we also have different receptors that can be exposed to these release materials, and these are human and environmental species that are in contact with this during the different stages. So during the synthesis, manufacturing, use, and end of life, you can have some workers, consumers, and that can be exposed to release materials during these processes. And then we also these emitted particles can be liberated in any of the environmental compartments if the processes they take place outside or in contact with any of the environmental compartments, which can be via the air, water, soil, roots, and ending up in the different exposure of the different species. Then how can we determine these releases along the life cycle? So we have to come up with the release rate, and we have to determine also the form of release. So if it's a nanomaterial, is an ionic form of the nanomaterial, is in the form of composite material, and then also to determine who is going to be exposed, so who will be the receptor, following which exposure route these release materials will end up to be in contact with these receptors. And for that, we have to do different monitoring of these releases for the purposes of quantifying, but also for the purposes of determine the properties of these release materials to be able to come up with all this information that we will need to finally determine the exposure. And for that, we have some possibilities of direct monitoring of these release materials during the activities or the processes that take place during the life cycle. But we also have to use some simulation methodologies that we can use as accelerated processes to simulate the real scenarios where these processes take place and simulating their characteristics to be able to control this monitoring of the release materials. For that, I showed you here some of the examples of processes that are simulated in the lab. Some of the instruments that we are using, instruments in which we follow standard procedures to determine what is the release form that gets it's emitted during the processes that take place during weathering, for example, during washing, during the use phase, these processes, abrasion processes, leaching and incineration that will simulate the end-of-life processes. So we have several processes that they can be lab simulated under accelerated conditions and following standardized methodologies. And of course, together with this and really linked, we do have to have the analytical methods to monitor the properties of the release materials, because the complexity of the release materials can be really high, because these nanomaterials can be embedded in different articles or products depending on what are their applications. So we need a combination of techniques, and here are some of the techniques that we are using in combination to be able to determine the properties. And here are some examples of quantifications and identification of these engineered nanomaterials emissions during the different life cycle stages. And these are examples of emissions that could end up in the environment, so at the different life cycle stages. And these examples have been run during different projects, Calibrate and Nanophase, and the release rates have been determined. So the data that we could get out from these experiments is showing here how we can get the release rate, release form, and the compartment where it will end up. And this information is all requested by the model, so we have it produced. And what we can learn also from all these studies is that there is a lot of determinants that are we have to consider in terms of influencing the release and exposure. And those determinants are mainly related to nanomaterial characteristics, the process characteristics, and also the if there is any system dependent variables, which means if we have risk management measures in place, the emissions will be reduced, and then there will be some calculations due to this needed to come up with the real exposure factors that we have to consider for the concentrations and identification of the release materials. Then this information, of course, is useful for read across and grouping, and all this data that is generated is, well, of course, compiled in release and exposure libraries. We generate templates for the whole community, so these templates are available via they've been generated in Gracious project, and now they are openly available for used in by the whole community in other projects. So we have these exposure and release templates with data in to be used for the models. So the key messages or the highlights highlighting the key steps for assessing release and exposure of nanomaterials and nano-enabled products are the identification of the life cycle stage, so the processes and activities that take place in this in each of the life cycle stages and what are relevant for the release and exposure, identification of parameters driving the release, and that means the properties and the characteristics of the nanomaterial, the characteristics and properties of the product matrix into which is the nanomaterial incorporated, and then also the type of activity and process that this nanomaterial will be going through during the stage of the life cycle. And then from all these, you generate a lot of data that is should be generated with standardized procedures and methods, and then collect this data in a harmonized way using these templates of release and exposure. And then the data will be used for modeling purposes, for validation, refinement of the existing models, and also for generating new predictive models for exposure assessment. So these are the highlights, and I thank you all for your attention and open for questions.
Hi, my name is Joris Quick, and I'm here to present a presentation on multimedia fate modeling, specifically on the model Simplebox for nano. Now, who am I? My name is Joris Quick. I did my bachelor and master's at the Wageningen University, and my PhD on aquatic fate of nanomaterials at the Radboud University, and lab work at RIVM. I did also a postdoc on aquatic fate modeling of nanomaterials at Wageningen University. Currently, I'm employed at RIVM, which is the Public Institute for Health and Environment, currently known for all the corona advice they give and so on, and research on that topic. But I work on environmental exposure assessment, mostly nanomaterials, but also other substances, microplastics, and so on. Also, I work on projects related to circular economy, sustainability, how to assess or those types of topics, specifically in the overlap with safety and risks of chemicals and compounds. Also, these are my views, not particularly those of the RIVM. So I'll be talking about a little bit introduction about exposure modeling, and then going into the details of Simplebox for Nano, how it works, what are the input parameters, the output parameters, and some examples of the model applications, some studies using the model, just briefly. And then in the end, there will be some slides and links to go to some further information if you really want to use the model or know more about it. So before we get into the modeling, when you want to know the exposure to a certain substance, it starts with an emission somewhere. You make a model, you use a product, these type of things. Then a substance can get emitted, or in this case, nanomaterials, to the environment. There they undergo different fate processes. They end up somewhere where there are organisms which are exposed. And if this exposure is too high, meaning you compare it to an effect threshold, to the safe level, then there is a risk, of course. Which is not always the case, but it's important to know the exposure to assess the risk. Now, actually, you can measure, of course, your concentration, which is, of course, done very often, monitoring different substances, monitoring their spread, and but that's, of course, after it's already been emitted. That's when you can. But sometimes it's very handy to know it beforehand. For example, if you want to allow a certain product on the market, or you think you can use a new type of material, it's very convenient to know beforehand what your exposure might be when you use it to a certain extent. So this is why modeling becomes quite interesting to apply this in prognostic risk assessment. For example, here we have a graph of Simplebox for Nano outputs on the left, which are calculations, predictions. This type of graph you get when you apply the model probabilistically. And of course, this is for microplastics, but of course you can also measure these concentrations of microplastics already because they're in the environment. And then you can compare them to the modeled ones and, let's say, start validating the model and so on. But this is not always as easy, for example, for some that are, of course, not out there yet. Now, what is Simplebox for Nano? So it's actually a screening level model. It actually calculates more background concentrations in large compartments, well-mixed compartments. In this case, focused on the environmental fate of nanomaterials, describing the process affecting fate. And so it predicts exposure, the concentrations in air, water, soil, and sediment. And it is built in a way that it has nested scales. So you have a global scale within which there's the continental scale and the regional scale. And in theory, you could add a local scale, but this is not part of the tool as it is right now. So Simplebox actually was an existing model. It's actually applied within regulatory frameworks such as REACH, and Simplebox was the basis for the EU's, the European Union System for Evaluation of Substances module on environmental fate. And so this makes it quite interesting to also make this fit for use with nanomaterials. Now, why would we need to make this model fit for nanomaterials? Well, the conventional Simplebox, or Simplebox 4, is of course fit for use with chemicals, but these are dissolved, for example, organic compounds, and they distribute themselves between the gas, liquid, and solid media. And this is described using thermodynamic equilibria with partitioning coefficients and so on. So for nanomaterials, it was found that actually because they are a particle, they're solid, they are thermodynamically unstable. So they will not follow partitioning coefficients known for, let's say, other compounds. Also, dissolution plays a role because they dissolve. For example, a nanomaterial is transformed to another form. Let's say you would have a dissolution of a silver nanomaterial, and you would get dissolved silver through dissolution, which is then the conventional form of the chemical. And there are other transformation products which are important, such as heat agglomerates, because they tend to aggregate these nanomaterials and stick together. So this adaptation resulted in different algorithms required, and one of the transport processes that needed to be changed was deposition, because particles have a mass. They actually can settle out of, for example, the water phase and the deposition from air to soil and water is also different. So also the solution, as I said, plays a role, and also the attachment to other natural particles. These were the main fate processes that were changed or added to the model specifically for use with nanomaterials. The other way was we could not use rate distribution coefficients, so we had to use rate constants, which describes the flow of the material from one form to the other, the rate. So in the end, when we look at transport, deposition was the main process that we changed, but advection, movement with a body of air to the next, through wind or flow of water downstream, this is still the same. Also related to transport between different compartments, there's no evaporation from, let's say, water or soil to air. There can be some resuspension, but this was found negligible and not included in the model. So these transformation processes are a bit more interesting. We included two types of aggregates. So basically, we call that heteroagglomeration when a nanomaterial sticks to another particle, a naturally occurring particle, because this is ubiquitous, right? We have aerosols in air, we have sand and particles in soil, and we have other suspended colloids and so on in water. So they attach to those, and we divided them in coarse heteroagglomerates and smaller colloidal heteroagglomerates below 450 nanometers. Then, of course, you have dissolution, where the specifically metals would dissolve. Of course, degradation can also be a process, particularly if you look into organic type of nanoparticles. Now, just to show a little bit of what is behind the model, I just show you how. So the model is basically built up of these rate constants, and dissolution. For dissolution, this is how the function would look, where you have change in concentration over time dependent on the dissolution rate constant and the concentration, right? For heteroagglomeration, it becomes a bit more complicated because there's not a heteroagglomeration rate constant per se. This is dependent on this big K, which is the collision frequency, the attachment efficiency, which is the alpha, and this is the efficiency and the frequency of collision between the nanoparticle and the natural colloid, right? They would meet, and this is the frequency that they would meet, and then the attachment efficiency is the efficiency at which they would stick together for the rest of their life. No, so these are two equations, one describing the concentration, change in concentration in time of the nanomaterial, or the change in concentration in time of the heteroagglomerate. Now, basically what then the model describes are three different particulate concentrations, those of the nanomaterial, those of the natural heteroagglomerate with the nanomaterial attached smaller than 450 nanometers, which when you look at the bioavailable concentration as a cutoff of 450 nanometers would be the combination of the two. And you have the total particulate concentration, which is also including the coarse fraction of heteroagglomerates. And then, of course, we also have the concentration of dissolved compounds. Now, the inputs required to run the model, they require an emission rate, so to the different environmental compartments, such as air, water, and soil, for a nanomaterial. We also require physical chemical properties of the nanomaterial. These are the size or the diameter or radius of the particle, the density, the attachment efficiency, the dissolution rate, and the Hamaker constant. The Hamaker constant is related to the interaction between a particle and another particle in water. So, of course, this is done for a certain landscape scenario, right? And this is, for example, the EU with a certain catchment, the Rhine catchment, which is, let's say, the default scenario in Simplebox. So you don't really need to input a lot of these numbers. There are already defaults given for you. But these characteristics that were changed for the nanomaterial model, Simplebox for nano, were that we needed some properties for the natural particles, such as size and density. Furthermore, these are all properties of the three different scales. We have properties of the lake, river, and seawater, 3 types of water, and agricultural, natural, and other soil. So another characteristic of Simplebox is that it calculates the concentrations in steady state. This means that the mass flows in between all the compartments are in balance, right? They're the same. There's just as much going into the compartment as going out. And this is done by a simple calculation. Actually, you take the inverse of the matrix of all the rate constants and degradation rates of the compound, take the inverse and multiply that by the emission, and then you have the mass in each of those compartments of that substance or nanomaterial. This formula, you can see that actually the mass and in the end the concentration, which is the mass divided by the volume of the compartment, is linearly related to the emission rate. Now, what is happening in steady state, it is not immediate, right? It can take time to reach this steady state. And for that reason, there's also a dynamic module, which you need to do currently. The easiest way to use the module is to do it in R with some R scripting. But what you get then is, for example, a calculation for each time point, and you can see what the concentration buildup in time is in each of the compartments. And on the right-hand side, I just want to briefly show this example, and this is again for microplastics actually, so not nanomaterials, excuse me for that, but they're particles nonetheless going with the same processes as nanomaterials. So what you see in the top here is that for example, the free microplastics reach a concentration, the steady state concentration within days even. But then the agglomerates reach a little bit later. And what you see here actually is that the marine run here does not reach steady state. Now, what I didn't tell you is the difference between the top and the bottom, which is the top ones are for microplastics that actually float and without any degradation processes and so on, or very high degradation processes in seawater. You can see that it takes more than 1 million years actually to reach this steady state, which is quite weird. Where if you have a fragmentation process, also these very light buoyant microplastics actually degrade, and you can see that within 100 years, almost 100% of the steady state is reached. So this is why it can be important to look at the dynamics of the system, and this is provided also by the model, although it's currently not. There are some software issues where we used to have a macro that actually did this, but right now it needs some manual tweaking in R to use. But the steady state concentrations are as simple as using an Excel spreadsheet to calculate. So this is another example of use of the model, or studying what the model actually means in terms of sensitivity to certain key parameters that describe fate of nanomaterials. So in this case, related to the dissolution of any type of nanomaterial actually. So what Joris Meesters did, he just varied these parameters and looked at the change in concentration that gave. And he saw that for dissolution rates above 10 to the power minus 12, the PECs were sensitive for the total range of particulates, so bigger and smaller ones. But he did the same for the attachment efficiency, which I briefly mentioned before, which is related to this heteroagglomeration with the particles, between different particles. So the nanomaterial versus the colloid or coarse. And you can see that it's sensitive to the whole range of tested attachment efficiencies, although the effect is different. In some compartments or some concentrations, the concentrations are increased when you lower the attachment efficiency. In others, it is the opposite. And these critical ranges are actually important to be measured, right? This is what you need to know. And this is also related to the test on how sensitive your measurement methods should be. And this is helpful in for regulating nanomaterials and their. In the end, Simplebox for Nano is aimed to be a regulatory relevant screening level multimedia fate model for nanoparticles. We have learned a lot from different projects in which we worked on the model. We have some more work, which I did not all present here. We continue to work on it mostly now in relation to microplastics. Of course, you should be aware that for predicting local concentrations, there are some adaptations required and some additional estimates of a local predicted incremental concentration, which the current Simplebox for Nano does not provide. So I thank you for your attention. Any questions or inquiries, please, my email address is given here. I cannot guarantee immediate response, but please feel free to contact me if you need any further help. So there is already an existing webinar actually from a few years ago, which might be quite helpful. They also provide some a bit longer talk on how to use the model, and also some case studies, which are also available in the model itself. So it's quite handy to actually have the model, click through it and look at that webinar, I think, if you really want to use it and still feel you need some help. The model itself is available for download on the RIVM website, so the nano version and the conventional version. GitHub, there's the link. You can actually find some of the scripts that are relevant for using the dynamic module, and there are several papers on the use of the model, the reports. So please have a look at these. Thank you again for your.
Hi folks, my name's Sam Harrison and I work at the UK Centre for Ecology and Hydrology. So I'm an environmental contaminants modeler, so I spend a lot of my time writing spatial and temporal models of how potential contaminants such as nanomaterials move around the environment. And today I'm going to talk to you a bit about a model that I was the lead developer on, and that's the Nanophase model, nanomaterial fate and speciation in the environment. So the Nanophase model is a spatiotemporal multimedia model. And what that means, so spatiotemporal, that means that it predicts things with spatial distribution by splitting up a geographical region into a number of grid cells. And it predicts things with temporal resolution by splitting a time period into a number of time steps. And it's multimedia, so what we mean there is that it covers different environmental compartments. So it covers soils, water bodies such as rivers and lakes, and bed sediments. We've been talking a lot about exposure assessment today, and so before we dive into the model itself and have a look at the model and its results, I thought I'd reflect on this question, which is basically why do we need a spatiotemporal model as part of an exposure assessment? So we've already seen from Joris Simplebox for Nano model. So the question is, why do we need something like the Nanophase model over and above Simplebox for Nano? And this idea of a tiered exposure assessment is one way in which we might need a spatiotemporal model. So if you have a look at this flowchart on the right hand side of the slide, this is a simplification of how a tiered exposure assessment could work. And the idea here is that you start off with the simplest but most conservative calculation of exposure and thereby risk that you can make, and that could be a simple back of the envelope type calculation where you make some really conservative assumptions like all of the nanomaterial released goes to one compartment and none of it transforms into other chemical forms, and you calculate a concentration based on that. And if you have some idea of hazard, you can then calculate risk from that. And because this is really conservative, if you calculate risk and it says no, it's not risky, then you know that you've kind of covered all bases and you don't need to do anything more. But if that simple calculation comes back and says, well, actually, there might be a risk, then you can go on to a more realistic model. And one example of that, as we've just seen, is Simplebox for nano, and so on and so forth. And the idea here is that basically as you move through these tiers, you're decreasing the conservatism, but you're increasing the realism of the model. And so as you get towards the higher tiers, like something like the Nanophase model, you have a more realistic picture of what's going on in the environment and what the real environmental risk from your nanomaterial is. But you don't want to start these really high tier models because they're complex and they're difficult to run and they require a lot of data. So I'm just going to quickly show you a couple of results that show you the types of things that you can get out of one of the higher tier model, something like the Nanophase model, over and above screening level or simpler models. And I'll do so using an application of the Nanophase model to the Thames catchment. And here we're splitting the Thames catchment up into 5x5K grid cells, looking at years from 2000 to 2020. And this is for nanotitanium dioxide. Because it's a spatial model, we can answer questions such as where are the hotspots? So we can split up a geographical region into spatial grid cells like we have here. And what this map here is showing is the Thames catchment. And the more yellow that a grid cell is, the higher the PEC, the predicted environmental concentration, is in the soils in that grid cell. So we're seeing the soil nanomaterial concentrations. And this is at the end of 2020, so after our 20-year run. And the conclusion we can draw from this actually is that the main determinant of the spatial distribution of nanomaterials is land use. So a key way that nanotitanium dioxide gets onto soils is through the application of sewage sludge, and that's higher in agricultural areas outside of our urban areas, which is why you see low concentrations in the urban areas like London and higher concentrations in the rural agricultural areas. And because it's a temporal model, we can look at the dynamics, and particularly we can look at the dynamics of more dynamically interesting compartments such as rivers and estuaries. So here, this graph on the right, I'm showing you an illustrative river reach and an illustrative estuary reach. And basically the main conclusion to draw from this is that the riverine nanotitanium dioxide concentrations are strongly influenced by the hydrology of the system. So you can see in the river all of these peaks, and those peaks occur during the drier months of the year. So drier months means that rivers are flowing more slowly and they're generally smaller, and because they're smaller they have less volume, which means that nanomaterials are more concentrated. Estuary, on the other hand, doesn't show as much a dynamic trend, and it actually shows a bit more of a trend that follows the emissions trend, which is shown at the top there. And the reason for this is basically because water can come in and out, up and downstream in an estuary reach, and this upstream motion has the effect of almost trapping nanomaterials in place, so you're not getting as much of a flushing through of nanomaterials that you do in river systems. So spatiotemporal models like the Nanophase model they give us lots of information, but this is at the expense of being fairly difficult to use. So because they're spatial, you need spatial data, you need temporal data, and this means they have high data demands, and often you need to calibrate them, and those calibrating procedures are quite difficult because you're calibrating over space and over time. And generally speaking, access to this type of program tends to be via the command line. You might need some program experience to be able to use them. So the general picture here is that you require some degree of expertise to be able to run this type of model. And that generally means that often the only people that end up running this type of model are the original model developers. But I just wanted, before I finish, I just wanted to reflect on some work we've been doing in a project called NanoSolveit to try and tackle this, basically by putting a graphical user interface, a GUI, on top of the Nanophase model. And what we're doing here, we're basically taking away a lot of the complexity involved in the model in terms of the data by fixing a geographical scenario and providing lookup tables for our nanomaterial properties. And then so all the user has to do is to come onto the application, which screenshot is shown is the screenshot is shown here on the right, and they can draw emissions on there. So they can put point emissions on there, which might be things like wastewater treatment plants, or they can draw areas, and that area might represent atmospheric deposition, or it might represent the application of sewage sludge. And then they can run that emission scenario through the model. And then, of course, you can also show the results of the model on the same interface, on the same map. And so really what we've done here is we've taken a complex model that only a handful of people can use and made it easily usable, such that, for instance, regulators could come along and put in their own emissions scenario and easily visualize the results from that. And this work is very much work in progress, but hopefully in the not too distant future, there will be a public version of this available for you to go and have a look at. And then finally, just a few conclusions. So today I've described what's quite a complex spatiotemporal nanomaterial exposure model, and given a little bit of information on how you might use that as part of a tiered exposure assessment. These models are traditionally quite difficult to use and required some degree of expertise, but there is at the moment very much a move towards simplifying their interfaces and giving them graphical interfaces to make them accessible to a much broader range of end users. Thank you very much.
Great. Thank you, everybody, for your presentations. Very exciting to learn more about this topic. So we have some questions in the chat. I think that one is going to kind of start being addressed. There's one from Carlos, which focus on the Simplebox for nano and mentioning 3 steps: deposition, dissolution, agglomeration. It also says, can it be used to aid for nanomaterial capture? I'm not very sure what is meant by capture, but I wonder if Joris has any ideas how to address this.
Yeah, I was also wondering what is meant by capture. Is that in terms of, let's say, what water treatment? In that sense, I think it's not really aimed at that. Although some of the processes are in there, I think they would be a bit more need to be tweaked a bit more, let's say, for a situation of water compartments, which you would see in water treatment. But I'm not sure if Carlos can elaborate on what he means by the nanomaterial capture.
We can wait a bit more if another question comes through. But in between, you can address the other questions. There was another one about the tool. I think the tool probably means the Simplebox for nano. I'm not sure. It could be the other one, of course. But you already start addressing the question.
So as I said, I don't have any numbers of how many industries, but in fact, you know, a lot of the chemical industry, they are not required of or should not use the Excel version for their dossiers. They should use the version provided by ECHA, which is EUSIS or within GESAR. But often still for research and especially, yeah, also industries can do that. The Excel version can be applied. Yeah.
Great, thank you. Yeah, do you want to add something else, or you're fine?
I just wanted to add that EUSIS and the GESAR tools are not adapted for nanomaterials yet.
Okay.
So the only way to do that is currently with the Simplebox for nano spreadsheet.
Great, thanks. And there's a final question about the nanophase. I don't know if you can see it, Sam. Is the nanophase model easily integrated with the usual chemical environmental dispersion models currently used?
Yeah, so it depends what you mean by environmental dispersion model. Is this talking about atmospheric dispersion or something more broader? I mean, I guess I can answer for an atmospheric dispersion model. So what we've done historically with the nanophase model is use a separate atmospheric deposition model, one called Lotus Eurus from TNO. And they've provided us spatial and temporal atmospheric deposition to the model, which is probably like the gold standard of what you'd want for this type of model. But that's not to say if you had other dispersion models that predicted deposition without temporal resolution or without spatial resolution, you couldn't provide those deposition rates to the model in such a way. But it would be slightly less realistic, but would still give you useful information. If you don't mean atmospheric models, I guess, I'm not entirely sure what you mean by integration here, but I guess the answer basically is that the nanophase model would predict environmental dispersion in its own right. So that's very much the goal of the model, is to predict, where nanomaterials end up in the whole terrestrial and aquatic environment.
Great, thanks very much. So I think we need to move on, because obviously with the few technical glitches, time has passed fast. So I pass on to you, Joris. Do you want to introduce the exercise, and then we can, I don't know, have 15 minutes or so, and then wrap up, come back to the general discussion. Okay, I pass on to you now, Joris. Yeah.
Sorry. Yes, sorry. I had to unmute myself. So I don't know if, unfortunately, I cannot see any of the participants or hear you, but I was wondering, I hope everybody is able to download the Simplebox for Nano model. The idea is that by going through a few questions, you get a feel of what the model does and how it can be applied. So actually, the first questions are not so much related to the nanomaterial fate processes themselves, but so I'm not sure how you can react to these. So maybe in the discussion forum or in the live Q&A, ask questions, because it would be nice to get a feedback when to proceed. Because so the first question is related, of course, to the PEC, which stands for the predicted environmental concentration, which in this case you can calculate, and if you go to the model itself, you can select in the input sheet the default scenario. And I don't know if maybe I should show you. So basically, you can first have to select the chemical itself, which in this case we selected the titanium dioxide particle from the Nanophase project. And then first it's very easy, it's just on the default scenario. And then you can actually see the output in the nanomicro output sheet. That's where the calculations go for the nanomaterials. All the outputs are shown here. But for now, we are only interested in the nanomaterial concentrations. So what it makes a bit more interesting is to, of course, use a scenario with actual emission rates as predicted by within the Nanophase project as well by EMPA. So when you select that, you can do that by going to the next scenario, which is the nanotitanium dioxide 10 nanometer realistic scenario. And if you do that, then it's good to have a look at the concentrations. And actually, so go to the output, and so my output is not what you should see, But if you look at the output, you should be able to see different concentrations for the nanomaterials. And what you should see is that I would like to point you to the concentration for the soil. Let me a second. And I wanted to know if you have any idea what the reason is that the agricultural soil concentration is actually the highest concentration. And I don't know if anybody could actually answer this or has an idea. And also please type if you say if you think it yeah, there's some sludge to soil. Yeah, exactly. So I think indeed related to it's related to the emission, right? So the emission rates to agricultural soil are higher because sludge is applied on average, not everywhere, but on average in regional, at least predicted in the regional scale, and this is higher than what is reached in the natural soils or in the other urban type of soil. So you should see, I think, something like this. Oh, sorry, I guess it's pretty small. So 0.007. So what I actually would like you to do is to then say, okay, let's set the emission rates exactly the same. So if you go to the input sheet and you go to these cells, you should be able to change them to so that's maybe I do it live with you. So you go to the input sheet and you go to the emission rates, and here you can see the difference in emissions. If you have it in front of you, you probably see it best, but you can see that the natural soil and the other soil are about the same order of magnitude, but the agricultural soil is actually 1 order of magnitude higher, the emission rate. So if we just paste that value, for example, to all of them, yeah, would you expect to have the same concentration then? So let's see. Well, actually, now the agricultural soil has the lowest concentration. And this is because we're looking at concentrations in the volume of the agricultural compartment within Simplebox, and this is looking at this regional scale, is the largest. There's more agricultural soil in the regional scale, which you can say is the Rhine catchment, than there is other types of soil, the other soil types. So the next question is if we can then, well, why this is the lowest concentration. I already answered that. And but the follow-up question is actually if you have any idea why this soil compartment is so big. And as I said, this is because there are more agricultural soil. And if you go to the landscape settings, this is where this is set in the model. So if you want to change the scenario to resemble a different spatial area, a different regional scale, you need to go and change that. So I would suggest that we change that to 0.323, because then it's an even distribution of the 3 soil types, just to see if we can get this concentration to be the same, because it should, if we have the same emission rate and we have the same volume. So we need to go down to the landscape settings here, and then there we have the fraction of natural soil, 0.323, 0.323, 0.323. So when we have done that, please have a look at the output. And we can see that they are close, the three concentrations, but they're not exactly the same. And the agricultural soil concentration is still a little bit lower. Now, why is this? Does anybody have an idea? Well, what is a big difference between the agricultural soil and other soil types? And well, I can't really see you, or if you're answering this, it's not in the chat, but of course, agricultural soil is cultivated and it's moved around a lot more. So it's plowed, for example. And this is why in Simplebox, the depth of the soil is there by default 20 centimeters compared to 5 centimeter soil depth in the natural and other soil. So let's say to see if we can get the same concentrations, I would ask you to make the soil depth now 5 centimeters. And this is not done in the input sheet because actually we assume that this is something that is quite basic to what is the difference between agricultural and the other soil types. But of course, it's because we have here the whole Excel sheet, it can be changed. So basically, you have to change in the regional sheet the mixing depth of the agricultural soil compartment. Here you can see default 5 centimeter for the other soil types at 20 for this. So if we make this 0.05, then it's the same depth. And to check, now we finally have the same concentration for all three soil compartments. Now this hopefully gives you a little bit of an idea on how to manipulate the landscape settings and how this then, what is behind this, especially for the soil compartment, but of course there's other aspects related to water and sediment and air. A bit more advanced question would be if you can combine landscape settings for, let's say, what describes the substance, the nanomaterial, or let's say the emission of the nanomaterial with the landscape settings for a certain area, because this was not actually changed at this point. But you could change it to the themes, for example, that Sam was showing in his presentation. And I just want to show how this can be done. It is not so, but it might be quite relevant. So basically, in the scenario spreadsheet are the scenarios which you select in the input sheet. So here you see the different headings. So you could make a heading combined, just maybe make it a bit more specific, but anyway. And you could copy the information which you want into these cells, where the theme scenario doesn't have any emission rates, but does have the area of the land of the catchment and the different fractions of different soil types and some other properties. So we could just copy those over. Make sure you have the right row. And of course, we need the emissions of, which are these numbers. And the zeros can also be copied over, but it's not, they should, for the emissions, preferably be copied over, because sometimes the default can be something different than 0, and then you're getting some weird results. So now, when you go to the inputs, you can actually go here and select, oh, not the chemical, the scenario. You select combined, and now it has changed not only the emission rates here, well, if we change these, of course, but also the landscape settings here, all the way down. Oops. These green ones. Now, what you should realize is that the model always uses the most left number. So let's say if the user column is filled in, it uses those numbers instead of the lookups, which for the themes are this, and in default scenario are this. when you don't change or add anything. So you can see that the number that is used, which is the dark gray column, are these. So if we want the tames, then we need to remove those. So this is a brief highlight of a part that actually doesn't have that much to do with the nanomaterial aspect of it yet. But when you look at the nanomaterial properties that affect predicted environmental concentration, these are really the radius, the density, the attachment efficiency, the solution rate, and the degradation rate constant. Now, it is, I think, handy when you want to use the model to kind of try and change some of these and see what happens. I think in sake of time, I will not do that in very much detail. But for instance, I can just show you briefly where this is done, of course. So all the way at the top, for this model, we put all the nanomaterial related properties in the top in this version compared to the conventional version, that of course does not include those yet. So rad S, this is the radius. Currently, it's 75 nanometers. And we could, of course, change it to something else. Let's say we want a very big particle. We say it's now 1,000 bit much. Let's say if radius right is the half of the diameter of 1 micrometer, 500 nanometers. The density, of course, is very important. It can be lower for a particle that is more complex, has other materials in it, has organic matter attached to it, and so on. So you can play with that. What is also very interesting to look into what's happening between the different species is when you change the attachment efficiency. Because what I was showing you just now is the total concentration of the S, A, and P species, which I illustrated in the presentation. But also, of course, the concentration of the free nanomaterials, the heteroagglomerates, and the large coarse heteroagglomerates are given separately. And you can see how this actually changes when you change the attachment efficiency. Because if the attachment efficiency, for example, if you put it to 0, which might be interesting to see what happens. And actually, I was almost surprised what happens, but then I'll show it to you. You would expect that no large or heteroagglomerates are formed because this prohibits formation of heteroagglomerates. But this is actually only true for the water and soil compartments. In air, the attachment efficiency is not applied because we use actually an aggregation model that is based on current aerosol dynamics models. So if you go to the output, basically what happens is there's a lot more of the S species, specifically in water, than it was before, and very, very low concentrations of A and P species. Only the sediments accumulate a little bit more, but this is the effect of that parameter. And you can do the same. One of the questions I wanted to ask is also if you can change it to 1, but also if you have looked at if you downloaded the model, there's a user guide which explains some of these parameters. And for example, it might be interesting to change the dissolution rate, because for now, for titanium dioxide, it's set at 0. And you should be very wary in how you change this. But for example, if you look in the user guide, you can see that this is the user guide that on page 9, there are some highlights given of what are the ranges that we expect this dissolution to take place in different compartments. So in fresh water, you would have within weeks or within months or no significant dissolution for titanium dioxide. And we kind of translated it to a basic dissolution rate constant, which you could apply for the different situations. So for example, you could also say, okay, I think titanium dioxide is dissolving a little bit. So you put a very low number, and this will mean a little bit is changed from the particulate phase to the dissolved phase. So these are the main parameters that you would change when using the model. What you need to be sure of, that actually it takes these dissolution rates and would fill them here by default. But if the lookup is 0, you need to be sure that if you want to use, for example, 1 - 7 here, you need to copy it down to all of them, or anyway, which particle you would like to dissolve at this rate constant. But a very simple approach is, of course, to assume that all the particles have the same dissolution rate constant. But this is not necessarily the case, of course. And this would then change what happens. And now it might be interesting to go to the all species output, because here you also have the dissolved species, which now also has a value because of this dissolution rate constant, and otherwise it's 0. So to wrap up, I would just like to thank you, and I hope it was helpful in a sense to get an idea. And if there are really any other questions, we can discuss them.
Excellent, Joris. I don't think there are any other questions. I mean, time is short now, but there's still some time. So if you have any questions, please add them to the chat. I think your illustration, it was really good to go through some of the points that were presented in the talks. It's a shame that time is so short and we're not seeing each other. Would have been really nice if we were. You would have been able, no doubt, to have engaged a bit more in dialogue. I know, Joris, that you've done this before with groups of people, and there's been quite success. You know, students and other type of delegates has been very successful. So that's great. Way of understanding the topic. I don't. Ooh, there's a hand up.
Okay. How does that work?
How do we? I'll be happy to hear from anybody. There's somebody with a hand up. If they can come in and say something. Okay, so they cannot come in and ask a question live. Okay, so yeah, folks with the hand up, please put your question on discussion forum. We still have time to address them or live Q&A. Let me just look at the discussion forum. No, there's nothing there new. Cannot see anything new, but if you can, Joris, please. Oh, yes.
Yeah. So Tam is asking, yeah, exactly. The default scenario is modeled after the Rhine catchment.
Okay, great. So I see that Sam is not in the room with us. Okay, he's been moved to the green room. Oh, yeah, you're back. So Sam, do you want to say a few words about the modeling or about any aspects we've discussed?
Yeah, my question, I was just curious, asking Joris about basically if you leave everything to default, what happens? And yeah, the Rhine catchment. But what about the nanomaterial? Are those properties of the nanomaterial for a specific nanomaterial as their defaults?
No, not a specific nanomaterial. So of course you need to enter something that resembles a material that you're interested in. Also, the emission rates are important to look at, because by default it's, I think, 1 ton to air, 1 ton to agricultural soil, and 1 ton to fresh water. These are just start-off values to calculate something, but yeah, a user would insert something that they're interested in. I think that question related to the emission, I think the emission is an important parameter that people usually either don't have or the only industry would know based on the production volumes. And this requires other types of modeling actually to estimate more the material flow analysis types of models. And I think people should realize that this also is an important part actually would be done before you apply a fate model.
Yeah, definitely. Models are only as good as their data, and in this case, as good as the emission and release data.
Okay.
Soko, of course, talked about this a little bit, right? Is measuring release rates and so on. So that's
exactly, yeah. So I don't see any more questions for the time being. So I just would like to wrap up, and you, Joris and Sam, are welcome to add also. So I just hope that you found this session interesting. We tried to give you some information on phyton exposure and why it is important. I do a lot of work on toxicology. Ecotoxicology is an area I'm very interested in. So working very closely with colleagues who do studies to assess exposure, concentrations, etc., is very important for me to understand that the studies that we do in the lab and potentially in the field that people are start doing now are realistic in terms of helping us understand that organisms are really exposed to concentrations and the forms they are exposed to. So this is a very important area. Also, it is important to understand where the nanomaterials might come from. So the idea of life cycle, what Soko was describing, is really important, you know, incorporating nanomaterials and formulations. So nanomaterials can actually reach the environment throughout this process. But then when the materials, the nano-enabled products are being used or at the end of the life, then what happens to them? So do they fragment if they are solid, say? Do they degrade, etc.? So this will help us again to understand. And of course, when they reach the environment, you know, Joris and Sam was saying, models really help us to understand that. So we haven't had a lot of time to play around with the model, but now you have it and you understand, I hope with Joris' explanation as well as the documentation, how you can play around with the parameters and see how change in the solution, even comparing to nanomaterials, for example, might have different solutions. The receiving environment will have a strong impact on the fate. So this is quite interesting, and I think it's something that you might be able to take your time to play around with a little bit and see how changes in the parameters affect the fate of these nanomaterials. So yeah. Sam and Joris, would you like to add anything? Are you there? Okay. I mean, if they can come back, there's still a couple of minutes. That would be good. Yeah, Joris is back. So, Joris, anything you like to say? Final words to wrap up, and Sam?
No, I am very. I would have loved to hear something if people have what their experience was with actually opening up the model and trying it out. As I think Sam also highlighted, you know, the user interface is an aspect that, of course, can be, is worked on more these days. And I think, it is also something we are looking at in terms of Simplebox moving away from Excel in a sense, but still Excel is for a certain group of people quite convenient.
Yeah, indeed. Sam?
Yeah, and just to say from my point of view, if anybody's interested in learning more or potentially even using the Nanophase model, do feel free to get in touch, and I'd be happy to set you on the right path there.
Excellent, thank you very much. And I also say goodbye from Soko. She had to leave a little bit early, but she really enjoyed being in the session. So no doubt she'll be happy to hear from you if anybody's got any questions in a part of the contributions. So that's us from us. So thank you very much for the invitation. It's been a pleasure. And we look forward to interact with you guys in the future, you know, just get in touch and yeah.